Great. Okay. So uh, let's start the class. Continuing the subject of solution concepts. And again, solution concepts in some sense are some kind of settlement cases or stable cases by some definition of a stable or settlement. So here we are continuing. I wanted to give one slide about correlated equilibrium, and then we will go to Maximin and MiniMax theorems and also solution concepts. So previous week we talked about correlated equilibrium, and we mentioned that that is a generalization of Nash equilibrium. Here, I just wanted to mention in terms of formula, it is not completely clear. I mean, like in terms of formula, there are some tricks that you need to know to use, such that you show that the Nash equilibrium is indeed a correlated equilibrium. So this is just one slide that or T.A. Suo has prepared, working with me on that one. So if you remember, this was the definition that we had it for. This was the definition that we had for correlated equilibrium. We said that take essentially all action profiles in which AI belongs to that. Then P of A, if you take this action and take the corresponding utility, if P of A is the landing probability for action profile. So this is the action profile essentially. An action profile means vector of actions. Mm. Good. So please avoid, I mean, putting chats, I mean, due to recording. Great. So here we have this one that for essentially all action profiles that A belongs to that probability of that action profile. This is the landing probability of that action profile times the utility that AI gets should be greater than or equal to. Again, we are taking on the same like overall A that AI belongs to A. Here again, landing probability of A. So far everything is about A, about AI essentially. And then here we take the utility of any other actions. So the landing probability in both cases is P of A. And P of A is the one that AI was included in it. So we don't change the probability distribution when we take these things. Now we want to say why Nash equilibrium is a special case of it. So consider a sigma to be any mixed Nash equilibrium. And as I mentioned, this is just the probability distributions over your, so this is like the two-player game. This is the essentially probability distribution that, so sigma is the probability distribution that assigned, I don't know, 0.5 to here, 0.1 here, and 0.4 here, versus here we have 0.5, 0.3, and 0.2. Here 0.4. So this is essentially sigma, the probability distribution. Now, if you consider any AI which is in the support of sigma, what's the meaning of that? It means that its probability is greater than or equal to 0. This is the definition of Nash equilibrium. What is the definition? It says that any action that you will take it in your support as a pure strategy, it should be the utility that you will get it. So in some sense, if you just choose this action and give the probability 1 here, then it should be better than or like greater than or equal to any other action that you will take in terms of utility. So here we just write that one. So here we will say that for we are doing the sigma over all a minus I, because here again this is the action profile of everyone else. So here we are like AI is taking a pure strategy. The probability is one, but everyone else is they are going according to their own strategy. So that's exactly this one. So this is the probability that we have it that this happens. And then in this case, if UI is taking the action AI, that should be greater than or equal to exactly the same sum, like all over all previous sum over all actions of others. Here the probability of others. This is the exact definition of Nash equilibrium times UI of any other actions that agent I is taking. So anyone in the support, essentially any action in the support, in terms of expected utility, uh, should be greater than or equal to the expected utility of any other actions. Now, this is just essentially the definition of Nash equilibrium. Now, you will multiply both of them by sigma of AI. What is the sigma of AI? Sigma of AI is essentially the probability that we are choosing AI. So we just multiply both things by sigma of AI. Now, let's set, uh, what was the PA? PA essentially was the, we can put it the probability of an action is indeed equal to sigma of AI times uh, sigma minus I of AI. And why do we have so this is the probability of A, and uh, in that case and note that it is important. So this is for Nash equilibrium. These two are independent. So these two are independent. So here, so you can actually this sigma of AI times sigma of minus AI, because these are independent, this is essentially is the probability of this, and this is the probability of this. These two are independent. So when you multiply them, then the probability of action A is indeed equal to probability of action AI times probability of all others taking action profile A minus I. So in that case, because these are two independent, that is by Nash equilibrium, we can actually, so this is again, this is P and this one. So this is indeed, this is equivalent. So we don't set it actually. This is the thing that we have actually. So we just set essentially P equal to sigma. Uh, so we just change the notation essentially to go to the previous notation. So here, for the probability, because probability of AI times probability of everyone else taking the action A minus I is equal to probability of A. This is essentially coming from and this is essentially somehow the intersection of these two things. Because this is independent, and we talked about independence before, then we know that the probability of this would be equal to probability of A. So we get essentially these equations that we wanted here. So, and this one, it is, and note that here we have both probability A the same essentially. And of course, then you can rewrite this one instead of say A minus on is all possibilities of action profile A minus on. You can just change it and they say that those action A that AI belongs to. And we get the equation that we wanted for correlated equilibrium. So this is the way actually you can show that the Nash equilibrium is indeed a special case of correlated equilibrium. Two things we are using it here. This is the definition of Nash equilibrium, and here we are using independence. That when we consider this one, then we can just say P of an action profile. So here in correlated equilibrium, indeed, this part and this part are correlated. They are not independent. But for Nash equilibrium, these are independent. Good. Okay. Okay. So today we are talking about Maximin and MiniMax strategies. These are some of the strategy profiles or some of the settlement concept that we are talking about them, in addition of other things that we talk like Pareto optimal, mixed strategies, Nash, or like pure or mixed strategies, Nash, epsilon Nash, and correlated equilibrium. So here, first we need to define the worst case expected utility. So for agent I, the worst case expected utility is a strategy, pure or mixed, which is the minimum over all possible combinations of strategies for other agents. So here we are taking all actions of others. What is the utility that agent I gets with a particular strategy SI? So let's see an example here, the husband and wife case. This was the normal form game, and this is the utilities. So here, for wife strategy, if it is P opera and 1 minus P football, and here for husband, we have it Q opera and 1 minus Q football, then the expected utility would be this. So essentially for each of them, we need to say what is the landing probability. Here would be 2 is the utility times PQ. So PQ is the landing probability and 2 is the 1. So you can compute it, and that's essentially the formula that we will get. Now, here, this is the important fact that we are using. If you are assuming P is fixed, then for any fixed or constant P, the formula above would be linear in Q. So if you put P equal to 1/2, then we get 1/2 Q plus 1/2. And here, whenever we have some kind of linear functions, if you limit it into two parts, we knew that Q is a probability, so it is between 1 and 0. Then we know that the minimum essentially or maximum happens at the boundaries. And here the boundary is Q equal to 0 or Q equal to 1. For example, if we have this P equal to 1/2, and this is the formula, then the minimum happens at Q equal to 0. Of course, Q equal to 1 would be the maximum. So we just write this formula. We just, in the formula above, we are saying that for wife, the minimum will happen, and this is over Q, because Q is essentially determines the strategy of husband. Then in that case, we are taking the minimum at Q equal to 0 and Q equal to 1. And again, you can just write the formula and see that. So that's the minimum that we obtain. Good. Now, what's the Maximin strategy or Maximin strategy? We are using both of them. So here, a Maximin strategy for agent I is a strategy SI that makes I's worst case expected utility as high as possible. So here we are essentially finding SI that essentially maximize this minimum. So we said that what is the strategy that I is taking such that the worst case, he or she is in a better shape or in the best shape. And that would be argmax. Argmax essentially reports that strategy that we say we call it S star I. It is not necessarily unique and it can be mixed. Here, agent I's max mean value would be essentially the, so if we takes s star I, what would be the value? So here, argmax reporting the actual strategy, while if you remove arg here, then essentially that's the value. So the max mean value or the security level would be maximum uh, over all strategies that I can take it. Then we are taking the minimum over essentially the worst case for all others that they try to minimize for UI. And this is would be the max min value or security level. For two-player game, it simplifies to uh, essentially this formula, maximum over S1 uh, of minimum over S2, U1 of S1, S2. Because here, agent 2 in some sense try to minimize U1. Good. Mm. Okay, so let's see the example that we had. So in the example that we had for uh, wife and husband battle of sexes, so here we had the strategy of wife and husband. And if you remember from a few slides ago, then the minimum essentially this was wife's worst case utility, taking essentially mixed strategy of Q opera and 1 minus Q football. So let's find P that maximizes this. So this is the formula, and we want to see what is the P that maximizes this. That essentially gives us the, um, so for wife essentially is, she was taking P opera and 1 minus P football. I think I mentioned Q, but for wife is P and for husband is Q. Okay, so let's just find a P that maximizes this. Anytime that we have essentially with the linear functions, it is very good actually to draw it. And we are drawing here. Even the previous case that we discussed, if we draw them, then we understand actually the minimum or maximum attains that boundaries that we talk previously. Now, if you just draw these two lines, and this is a general idea, when you try to minimize something, generally to weigh, and this is the minimum of two things. Generally, the idea is that if you take them equal, that's the one that's the minimum or maximum happens. So why? Because the idea is that you are just drawing these things, and you know that this kind of vertex that we call it in linear programming, that will happen when two lines intersect. And these two lines intersect means that this is this line, this point is both in the this line and on this line. So it means that you should just put this value essentially put them equal. So I will just put 1 minus p equal to 2p and obtain p equal to 1/3. So here, and always you should check because this would be minimum or maximum. But in this case, essentially, it would be the maximum value. So Wife maximum value would be 1 minus p. Uh, okay, so just one thing. So here, p equal to 1 over 3 would be the essentially the maximum strategy. So p here should be 1 over 3. Now, what is the max min value? Wife's max min value here, because by definition, we put them equal. So it would be 1 minus p, minimum of 1 minus p and 2p, but these two are equal. So the wife's max min value would be 1 minus p, which is 2/3, or 2 times p, which is again 2/3. So the value, so this is the value. So the max is this, and the value is this. Uh, and so you see the value is 2/3. this essentially rings the bell. If you remember, we had such kind of things. We had similar things when we talked about Nash equilibrium. But we will, in terms of value, not necessarily strategies. What about Wife's Maximin strategies? So in that case, would be one-third opera and two-third football. This is essentially you just put the P equal to one-third. Similarly, for husband, you can just do all these calculations. The Maximin value would be two-third for him as well. And the husband's Maximin strategy would be two-third opera and one-third football. So here, let's do this one. So here is one-third opera and two-third, sorry, here for wife would be one-third opera and two-third football. And for him would be two-third this and one-third. Good. So just look at this one. That is actually interesting. As I mentioned, in terms of value, is this two-thirds the same thing that we had it for Nash equilibrium, mixed Nash. However, in terms of strategy, actually is quite different from the other one. So if you remember, in the Nash equilibrium, actually they take it the one that they like the most. They take it two-third opera and one-third football. And here he was taking two-third football and one-third opera. And these are essentially for mixed Nash. Versus here, essentially, versus here, which is the so in the Maximin, we are essentially the strategies that they are computing would be somehow the reverse of Nash equilibrium. The value is still the same, interestingly or surprisingly, but the strategies are different. So in the Maximin, you actually taking the wife is taking two-third football here, the one that she does not like it. The same thing for husbands. Good. So here, in this case, the Nash equilibrium and mix are not the same. And we will go there. And we will discuss that when max, mean, and essentially Nash equilibrium would be the same. Good. So let me just clear everything. Good. So this was the value that we have. So this is the question. Essentially from the game theory incentives that we always talk about it or practical sense. Why an agent I want to use Maximin strategy? So of course, if I is very cautious, it somehow does not want to take the risk. This is a very good one because this is something, this is the guarantee, as I mentioned, it we call it a security level. So if I don't have any other information about the others, I don't know what are they, I want to just make sure that my security level is as high as possible. Yes, it might be, I mean, not the best case, but I want to say that I will not be in the worst setting, essentially. For example, a strategy that you may take in some of this financial setting, essentially. A bank wants to make sure that in the worst case, it does not become bankrupted. And this is good because I don't have any information about the other, whether they are rational or not, what are the payoffs, and whether they draw their action choices from known distributions or unknown distributions. I don't know anything, so I just want to maximize my security level. So, and more interestingly, as we discussed, this might be also useful if we know that agent I has reason, agent one essentially has reason to believe that other agent's objective is to minimize I's expected utility. It might be not always the case, but in particular in two-player zero-sum game that we will discuss, this will happen essentially. That in some sense, if the other agent try to maximize his or her own strategies, would be equivalent to minimizing for I utility. So in that case, actually, taking the Maximin is a good strategy. And we always have this solution concept. What is the Maximin strategy profile? This is a vector of them. Again, all players are using their Maximin strategy. So essentially, it's a strategy profile that, for example, if we have two players, this is the first things, and this is the, by a star means generally means optimal, essentially, or the best choice. Good. And let me define the other one before go essentially to the Nash equilibrium, considering these concepts in more details. So a Maximin strategy in a two-player game, we are defining it for general, but it is especially interesting for two-player game. So here a min-max strategy or min-max value is a dual of Maximin essentially strategies or profile or value. Say agent 1 wants to punish agent 2, regardless of how it affects agent 1 own payoff. So you just want to essentially make the scenario worse for the other person. So this is like you can consider essentially terrorist activity. That, I mean, player is wants to just, independent of what will happen to itself, just want to make the situation worse for the other. As I mentioned, and as I discuss more, in two-player zero-sum game, actually these two would be the same. So we will discuss that. These two concepts would be the same. So here, agent 1's Maximin is a min-max strategy against agent 2 would be like this. A strategy S1 that minimizes the expected utility of 2's best response to S1. So what would be that? So here, min-max would be the argmin of S1. So you take the strategy such that you will minimize the best case for agent 2. Here, this max essentially is the best case for agent 2, and we are taking the utility of the second person. If the strategy profile is S1, S2. So here, agents 2's max min value would be, of course, the value of this is the 2's maximum expected utility if agent 1 plays his or her own min-max strategies. So essentially, again, this would be some kind of S star 1 essentially. So agent 2's min-max value would be essentially this that we discussed. So argmax reporting actually the actual strategy that attains it, and the value would be this. And you can similarly define min-max strategy profile if both of them, again, are using their min-max strategies. So this is somehow the dual counterpart of Maximin. Good. Let's see the example essentially for the game that we had it. very similar computation to the previous case. So here again, consider wife P1 minus P here, and then Q and 1 minus Q here. Then in this case, what about for husband? What if the husband PQ? Because you said that essentially here U1 and U2 will change essentially here. See, here we are talking about U2 for min-max, but before we were talking about U1. So that's the difference between essentially max-min and min-max. Now let's go back to this one. Okay. Now, so we just write for husband, for PQ, what would be the utility? Again, you just compute the landing probability times the utility at that time would be this formula for this. This is the expected utility. Now, we are doing the same type of argument. Given wife's strategy P, husband expected utility is linear in Q. So if you are assuming P is fixed, then the husband would be just linear in Q. So for example, if you put P equal to 1/2, then it would be, if you compute the things, would be minus 1/2 Q plus 1. So it would be linear in Q. So again, the maximum here, it will be obtained at Q at the boundaries because it's a linear function. So the maximum would be essentially the case that Q equal to 0 and Q equal to 1. So the maximum would be essentially the so the maximum would be equal to the max, essentially the it will be attained at either 2 minus in these two lines, essentially this line or this line. And now to minimize, so these are the two lines that we have. Now here you want to find the P that minimizes this, because we are talking about the minimax. Again, we are putting equality. As I mentioned, when you put the equality, sometimes it finds max, sometimes it finds min. You should always check if you draw it, I mean, with hand or with some of the software, you can actually see what will happen. That would be an easy way to do that. So here the minimum would be when you put this equal, then P would be equal to 2/3. And you can see that the husband min-max value was P, so it was 2/3 here. So here, P would be 2/3 for essentially, yes. So just yeah, so this is important. So here, husband's min-max value would be 2/3, and wife's min-max strategy would be essentially 2/3 opera and 1/3 football. So this is important. Here we are talking about husband min-max value because it is U2 that was in the formula, if you remember. So we had the min-max U2. So that's the thing that we need to talk about husbands, essentially, min-max value. But here we talk about wife's min-max strategy. And why? Because we were talking about P. And here, we are talking about wife's min-max strategies. And it is 2/3 opera, 1/3 football. So that actually is the same as we had it for Nash. So you can, so this is essentially, in this case, wife is doing 2/3 opera, the one that she likes more, versus the previous case that was doing 1/3. for Maximin. And you can compute the same thing for husband as well. That would be the same as Nash that we discussed. It means that 2/3 football and 1/3 opera. This min-max strategies that we discussed, that actually can be generalized for any number of players, which is even more than 2. But the issue is that when in an n-agent game, then if there, like here we talk about S1 and S2, and for example, first player try to make the situation work for the second player or vice versa. But if you have n agent, then one agent alone cannot try to maximize the utility for another person because there are other players other than these 2 players there. So that's the issue that we need to use the idea of gang up. So essentially, a set of agents may gang up against one particular agent. So here we define S star minus J, we mix a strategy profile that minimizes J's maximum value. And this is essentially is the one that played by all other players. So here, all other players, all players except J, they need to gang up to find their strategy such that they will ruin the case for one particular agent. So you can think about this one in real world would be like sanctions, that a set of countries or set of parties, they are putting a sanction against one person. So they try to find a strategy that essentially hurt that agent the most. And in this case, for every agent, I not equal to J, a minimax strategy for I would be I's component of S star minus J. And again, the value would be the value that essentially attained by this optimal strategy. So it would be essentially the here would be essentially the one that minimizes like over. So essentially, this is the payoff of Sj if they are taking Sj, and we want to find that minimizes for them. Good. So that will be equal to this. And we have yeah, so we want to essentially, so this is the part essentially that we were so we always actually, this is not equality necessarily. So this is the one that the J's minimax value would be the one that the Sj star that attains the minimum for this, and that would be this. And then we have equality when if we replace essentially here by this. Yeah, so this is actually the thing. We have actually equality. Here, let me just. Yes. So here, note that like here we had S minus J, and here we have S minus J star. So if we essentially, to just replace this in the formula, the one that essentially a strategy profile of all others than J that minimizes this. So if you put a star here, that would be essentially, it is equivalent of this essentially. Or you can simply just remove this arc and you get the value. So whenever you want to get the value, just forget about the strategy, just talking about the value. Good. So this is a very important minimax theorem that you will hear a lot. That What is this? Let G be any finite two-player zero-sum game. For each player I is expected utility in any Nash equilibrium. So if we have essentially two-player zero-sum game, this concept of Nash equilibrium, Maximin and MiniMax, all of them will collide to the same thing. So here, in particular, I's expected utility in any Nash equilibrium would be I's Maximin value and I's min-max value. In terms of formula, if you consider a Nash equilibrium S1 star, S2 star, then the utility of the agent 1 in this Nash equilibrium would be a one that actually is the one that minimizes the maximum for the other person. And this is the same one that maximizes for the first agent. And that would be equal to, and here this is we are talking about the zero-sum game. So here, U1 of S1 star, S2 star is actually equal to minus U2 of S1 star, S2 star. So that U1 of this would be equal to minus of this, because it is a zero game. So as a corollary, for any two-player zero-sum game, we have this concept of Nash equilibrium, max-min strategy profile, and min-max strategy profile is the same set essentially. And this is not necessarily correct for non-zero-sum games, because as you saw, essentially, the min-max value and the max-min value were different there. And just one of them was actually equal to Nash equilibrium in this case. And here, whenever we talk about the value or min, when we talk about the value or min-max value, essentially is for a game is the agent one's min-max value. So that's the one that, I mean, this is the value essentially, which would be this. But we are talking for the agent one. Now, let's see why we have this essential equality. This actually comes as part of a duality theorem. So this is the duality theorem for linear program. That we talk about it. So we can read more about the dual, but generally this is the idea. Whenever you are writing a maximization problem as a linear program, you can also write a dual of that, which is a minimization problem. And there is a way to obtain it. You can actually read it. This is a very classic way that if you are given an LP, you can write its dual. You can write even a program that produces that. And the important thing is that the value of the essentially the original LP and its dual, one is maximization, the other one is minimization. These two are equal. So that's the interesting thing about this duality theorem. Good. Let's go for the next one. So max-min or minimax via LP, essentially. How can we obtain this? So this is also interesting. So another interesting thing is that Nash equilibrium in general for two-player games is, I mean, it is p-pad complete. So even for two-player, as we discussed, we cannot find the Nash equilibrium. However, in two-player zero-sum game, because all these three concepts of min-max and max-min and Nash equilibrium are the same, actually we can solve the problem via linear programming. So linear programming plays a very important thing again here. So let's define this one. Let's see how can we write a linear program that obtains it. So we talk about a linear program that can obtain correlated equilibrium. Now we are talking about a linear program that can find the min-max or max-min or Nash equilibrium in zero-sum case. Good. So let's go through this. Okay. Let's define U1. Essentially, so here, because it's a zero-sum game, we can assume that U1 is equal to U and minus U2 is equal to U1, because again, this is a zero-sum game. And so it is pure competitive game. So we assume U is the utility function for the first player. And let's mix strategy S1. So for first player, say this is the strategy things. We are considering two-player game here. So X is essentially the probability distribution, X1 to Xk. K is the number of actions. K is the number of actions of agent 1. Agent 1. Similarly, assume S2 equal to Y equal to Y1 to YR. And R is the number of strategies of the second player. Good. Good. So this is the definition. This is the first probability distribution. This is the second one. Then what is the U, your expected utility for this? So this would be essentially the landing probability, xy times yj, the utility that agent, like the first agent or second agent gets. And here in this case, we talk about the first agent. So it would be xij, yij, xj, xiyj, uij. And here, because the yi is an independent variable in this thing, yj, we can actually, yes. So here we can write this one, essentially just change the order of this sum, and then write it this way, that it is sum over all j yj, then summation over all i's xij. So this is formula is just simple math that we are doing, or simple algebra. So now we want to find x star. This is the optimum s star, which optimizes v1. What is the v1? Essentially is the one that, say in this case, we are trying to maximize x's minimum over this. So this is the security level or max-min strategy for agent 1. So now, since player 2 is doing his best response in this, so whatever strategy the first agent takes, whatever x that essentially the first agent takes, agent 2 is doing his or her best response in the minimum, because it tries to essentially see what is the one. And here, why minimum? Because it's a zero-sum game, and essentially if she's doing minimizing for the other agents, it means that U is for the first agent. It means that it maximizes for his payoff. So here, player 2 is doing best response in here. So it means that if yj is greater than 0, then this should be minimized. So this is similar to this, again, GPA paradox that I was talking. So it does not make sense to put yj greater than 0 in this sum if this xiuij is not minimized. Because, I mean, here we have yj times that. So you want to just put the mass on something that is minimum, because you try to minimize essentially this. So you only do it if this part is, the second part is minimum. Otherwise, you can just move it, your strategy, and put the mass on the one that is essentially minimizing this. So then in this case, we can just write this one. So V1 would be this that we talk about it. This would be equal to, So we know that, as I mentioned, yj is taking greater than 0 if this is minimized. It means that only those, if it is greater than 0, all of these terms should be the same value. So all of these terms should be equal to actually to minimum. Because as I mentioned, anything which is not minimum, it will be removed. Y does not put any math there, does not put any non-zero values there. So anything that remains should be equal to minimum. That's the thing that we can replace this part. So here we had this one, but we just replace this one with the minimum. And this is the minimum would be the same value for all of them. And now what is the sum of the yj? That would be equal to 1. So that would be equal to this. And we know that, of course, this minimum should be less than or equal to this for like it. So this minimum j should be less than or equal to this sigma for any j, because by definition, this is the minimum. So what is the formula? So this is essentially, we just write this formula. Now we have an LP for this. We can write essentially this LP. What do we want to do? We want to maximize the value V1. So we say that maximize V1 such that V1 is less than this. Again, the last one was by definition, essentially. So we have written this equation. We said that V1 should be less than xi uij for all j's. And of course, this should be a probability distribution. So it means that xi should be equal to 1, sum of the xi's. And xi should be greater than 0. So this is somehow similar to the thing that we have done for this husband and wife, but you can actually write it more formally here. So this is the LP. So this is the final LP that you can write it to find uh, essentially V1 value. And of course, if you know the value, then you know who has obtained it because you know the value. So you can find also the strategy profiles. So you write essentially the one that maximizes this. And of course, if you solve the LP, you know what would be the strategy xi this. So this would be the one that essentially the maximin for x. And this is a very simple LP. This is the mainly comes from this equation and a little bit of reasoning here. And this one is simple. It's just a probability distribution. So these two are just a probability distribution. And this one is so that V1 should be less than that, and we want to maximize it. Good. So similarly, you can write these things. So similarly, you can write the V2. V2 is the, so far we have written it for, see here, we had it for maximin. Then we can write the same thing for min-max. So again, now we call it V2 essentially. So V2 is the one that is the min-max, but again for agent 1 essentially. So there you need to change essentially. So here, this is important. Here we had it, we had XY. See, the order was min X and min Y. Here we have it differently. Here we have min Y. Here we have min Y max X essentially. But still the utility is the same. For before also we had u, here we had u, because we are talking for the first agent. So we write essentially max min, min max, and you can write exactly the same equation that we had. Now you could say the same thing, that now instead of every reasoning that we had it for mean, that if yj is greater than 0, it should be mean that yj, the same thing you should say that for max, and the things that you will get it would be this LP. So in this case, actually, you can also find, so you can write this one. And due to min-max theorem, and as I mentioned, min-max theorem here would be essentially the duality. So there are several things that are all the same. So it is min-max theorem, the duality theorem, sometimes it's called Farkas lemma, essentially, for linear programming. All of them, so Farkas lemma, duality, and minimax, it says that the V1 and V2 are equal. And here, I mean, it is easy to see V1 is less than or equal to V2. I mean, because essentially by definition, so one is taking the minimum, for example, the other one is an arbitrary strategy, and that would be the case. But the equality would be non-trivial, essentially. And here, when you compute this one, so what is the interesting thing is that in the previous LP, we could get X. In this LP, we could get Y, and now X. So you will get essentially one for the first player when we have written. So in this LP, the variables are X essentially. So you get here X essentially for the first player. Here the variables are Y, so you get a strategy for second player, and as a result, you can just put these things, S1, S2 equal to XY, which is a Nash equilibrium. And these are all essentially, these three theorems are the same. You can see the proof of that. I mean, the proof is not a trivial one, that why we have the dualities for LP, but you can read more about it and see that. But this is, if you write it, as I mentioned, there's a very concrete way to write a dual of that. If you write the dual of this, previous person, then it would be this, and vice versa. If you write the dual of this, would be that. And here in the first one, we have the max. For the other one, we had mean, essentially. Good. So let me just finish this one. So this is one example that I wanted to just mention for matching pennies. So if you consider the matching pennies, you can again define this one. Agent one strategy is that P heads 1 minus P tails, and then Q heads and 1 minus Q tails for the second strategy. You can write the U1, U2 is very similar. You just essentially compute the landing probability times the utility. And because this one is a zero-sum game, because like if you see each of them, the sum of them would be zero, the sum of the utilities. Now, for this game, we know that the Nash equilibrium is equal to Maximin strategy, min-max strategy profile. The set of them are equal, and this is the one that we discussed, P equal to 1/2 and Q equal to 1/2. So that's essentially a mixed Nash and min-max and essentially Maximin for this. And so these are, I mean, some of the computation that you can actually go and try to read it. And you can see essentially, so like you can see, this is one of the things that I mentioned. You can always draw and see it also in the picture. For example, here you know that P equal to Q equal to 1/2 essentially is the max min or min max, but you can see on the essentially on this diagram that why this is also a Nash equilibrium. So the idea is that essentially, if you are at P equal to 1/2 and Q equal to 1/2, no one wants to change the strategy, because here essentially this kind of saddle point of this essentially curve. But as soon as you will change your strategy, essentially then you will go all the way to zero essentially. So in some sense, you are in the best place here in this saddle. And if you just change a little bit the place, then you will fall essentially. That's the meaning of Nash equilibrium. And you can see the calculations here. And it is also, again, from this diagram, actually, you can argue that there is no other Nash equilibrium, because if there is any other place here, this is, again, the one that if you see the diagram, it would be much easier actually to see. You can see that if you change your position to any other place, you will consider there is always a way to fall essentially through this. So that's the only Nash equilibrium that exists for this case. So the set is the same as essentially maximum value and min-max value. And you can say that, I mean, you can compute the max min value for them or min max value, and this is a unique one. So as I mentioned, so you can actually compute this one, the min max or max min, the same way that we have computed for this husband wife battle of sexes, and you see that then you will get P equal to 1/2, Q equal to 1/2, and essentially the same thing. So in some sense here, essentially, I'm just finishing to say that for this particular case of matching pennies, which was a zero-sum game, you can actually compute min-max, max-min, the way that we have mentioned, and the Nash equilibrium that we discussed before. And you can see it actually, I mean, even the diagram will be useful in some sense. In several places here, we have seen that if you have a diagram, then you can argue much easier, or like you can have a much better essentially ideas about this, and or intuition about it. So using that, you can show that there is a min-max and max-min and Nash equilibrium. There is only one point, this saddle point essentially, and and there is no other strategies for min-max or max-min or Nash equilibrium. So there is only one, and what is that? It is 1/2 heads and 1/2 tails essentially. That's the one, and I'm finishing here.